today's lecture session, we are going to start with dynamic logic. It's a continuation of the previous class where we have seen the introduction. It is a basic principle of dynamic logic. Now we are going to continue with that logic. Pre-charge. So two phases are going to be there. So pre-charge phase when clock is equal to 0 and evaluation phase when clock is equal to 1. So what happens at the pre-charge? Dynamic gates use a clocked CMOS pull-up. So thereby the transistor is on and NMOS transistor will be in off condition. So that output is always high. So this can be understood by means of the circuit. Just we'll go into the circuit. So look into the circuit where pull down network is going to be with NMOS transistor. It's a logic implementation. But when you go with the pre-charge phase, clock is equal to 0. So this particular node, the output node is charged to VDD. So this is pre-charge. Why we call it as pre-charge means output node is charged to that value. And evaluation is going to start when implementation is going to be there. It's a logical implementation. It can be a Boolean expression. So here we have taken a typical example of A dot B plus C complement. So for that function, we have gone with a dynamic design. Conditions. So what all the conditions we are going to have with the dynamic design. So look into the conditions. The first one, once the output of a dynamic gate is discharged, it cannot be charged. So that is the first condition we have. And second condition, inputs to the gate can make at most one transition during the evaluation phase. So it means that always a high to low transition will occur during this logic implementation and output can be in a high impedance state. So this already we have seen in the introduction part where the node CL, it is going to be held at a high impedance state. So these are the conditions. Now we go for the features. So what all the advantages we have with the dynamic design? Faster switching speed. Just look into the faster switching speed. Why we have faster switching speed? It is due to the dynamic switching activity. So switching occurs only with respect to a clock signal. Thereby a reduced load capacitance will be there, which in turn reduces the logical effort in the particular design, and reduced load capacitance due to fan out. And here we don't have any short circuit current. So this is a basic difference what we have with static and dynamic. So short circuit current will not exist due to the switching activity and ignoring the influence of pre-charge time. So where the time taken for a low to high transition, but the presence of the evaluation transistor slows down this propagation delay where the transition is going to be between high to low. So these are related with the switching speed. So when you look into the switching speed, everything it is related with the capacitance effect. So here it is the internal and it is an external capacitor and this is a load capacitor. And at last we have a propagation delay which is existing between the low to high and high to low transition. And now coming to the power dissipation. So power dissipation, it is of important when you go with static and dynamic. So when you take a dynamic circuit, so here there is no short circuit path which is going to exist between the pull up and the pull down network. Thereby it consumes only dynamic power and no static power in a particular design, and lower CL as well as the internal capacitor. So fewer transistors are connected. So this fewer transistors only we have seen in the special features of a dynamic design where we have a MP transistor and ME transistor, and the logic implementation it is by means of a NMOS. And the last point, it is related with, here we have a construction which is related with at most one transition per cycle. So it implies that no glitching takes place. So glitching is nothing. Glitches are the unwanted signals, so which is going to be raised. So we have studied about static dynamic glitches. So here with this glitching concept, as well as only dynamic power utilization, and fewer transistors are going to be used. If fewer transistors are used, then power consumption is also less. At last, the pull down network starts to work as soon as the input signal exceeds a particular threshold voltage. And we have a mid-band voltage Vm, so which relates with the low noise margin concepts. So with this, we just conclude the features of dynamic design. Thank you.